In this video, we're going to be looking at how parametric equations apply to real-world situations and solving them. So let's take a look at a parametric equation to model projectile motion of throwing something, hitting a ball, kicking a soccer ball, hitting a golf ball, things like that. So we've got this horizontal movement and we've got the vertical movement that happens when you hit or kick or throw something, okay? So you've got the path that the actual ball is traveling or object is traveling, and you can break it down into a horizontal distance or a vertical distance. So the horizontal direction, or the horizontal equation, is going to be the velocity, okay, or the speed, the initial velocity, times cosine of the angle that it's moving off the horizontal, times t, plus the initial horizontal movement. So x naught is the initial horizontal position. Okay, so velocity times cosine of the angle times t. So t is going to be your variable. So this is just going to be something you're going to plug in and get a decimal, plus the initial horizontal position. And then your y, or your vertical movement of that object, is going to be negative 16t squared plus the initial velocity times sine of the angle times t. Again, t will be your variable, so this is going to be a decimal. And remember, y value goes with sine, x value goes with cosine, okay? So in this one, then you're doing the velocity sine of the angle t plus the initial vertical position, okay? So y naught is your initial vertical position. So then let's take a look here, okay? So baseball problem. So Brian Dozier hits a baseball when it is 3 feet above the ground with an initial velocity of 110 feet per second. The ball leaves the bat at a 35-degree angle with the horizontal and heads towards a 15-foot fence that is 340 feet from home plate. Okay, so let's just draw out this situation a little bit. Okay, so here's where he's standing. Here's home plate. He's going to hit the ball. Okay, now when he hits the ball, okay, where he hits the ball, it starts 3 feet above the ground. Okay, and then the ball is going to, travel somewhere. Okay, then we've got the horizontal distance to the fence. Okay, and then there's a fence here, and the fence is 15 feet tall. Okay, so we got the fence. In baseball, if you hit it over the fence, right, it's considered a home run. And if it doesn't go over the fence, then it would not be a home run. Okay, so this fence is 15 feet tall, and the fence is 340 feet from home plate. Okay, and then again, the bat here is 3 feet off the ground. So where he hits it, it's 3 feet off the ground in line with home plate. All right, so let's break down a few of these things. Okay, so you've got also an initial velocity here. Okay, so your velocity vector, or your initial velocity, is 110. You've got your angle that it left the bat, that's at 35, okay? So let's go ahead, and you can solve either the horizontal or the vertical equation first. This one is much more difficult because of the t squared, so this is a quadratic. So I start with the horizontal, okay? So let's take a look at the horizontal equation. So remember, the horizontal equation is the magnitude, or the velocity, the speed, times cosine of the angle times t. And so we know the initial velocity is 110. We also know the initial angle, okay, the angle that it left the bat at. And then this t is kind of what we're looking for, because it is in both the horizontal and the vertical equations, okay? We actually know how far this ball would travel if it were going to hit this fence, right? So we know the horizontal distance that we're looking for because we're trying to see what happens at this fence, Okay, is the ball 15 feet above the ground when it gets to the fence? Okay, so the ball is 340 feet away, so we know that distance. Okay, so we're just going to solve this equation for t and then plug t into the vertical equation. Okay, so just type this into your calculator. So make sure that your calculator is in degree mode and do 110 times cosine of 35. And you'll get 90.1067 blah, 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 t. Divide both sides by that. Okay, so divide by 90.1067. And that will solve for t. Okay, so when we do 340 divided by 90.1067, you get 3.77 equals t. So what this means is it took this baseball 3.77 seconds to go 340 feet horizontally. Okay, not how far did the actual baseball travel, because it's going up and down and traveling a little bit of a different length. It's horizontal movement, okay, to go 340 feet. That is going to take this ball 3.77 seconds. So now what we'll do is we'll plug 3.77 into our vertical equation, okay, into the y part to see how tall or where is the ball's height after 3.77 seconds. Okay, so the equation here is going to be negative 16t squared plus plus the velocity times sine. Okay, so the velocity was 110 sine of 35 times t plus the initial height. Okay, and the initial height when we hit this ball was 3 feet above the ground. So now you're going to go and just plug in 3.77 into here to see what the height was of this ball after 3.77 seconds, to see if the ball was high enough to clear the fence. Okay, so negative 16 times 3.77 squared, so 3.77 squared times negative 16, and you can just type this all in at once if you want to. I'm just going to write it out in chunks. So this would be negative 227.4, and then you'd have 110 times sine of 35 times 3.77. So you get 237.86 and then plus 3. So just add all of that together. And you get that the height of this ball after 3.77 seconds is 13.46 feet. Okay, so what this means is once the ball got to this spot horizontally, once it got to 340 feet right here, the ball is at 13 feet. Okay, the height of the ball after 340 horizontal movement is at 13 feet, 13 and a half feet. Okay, so did the ball clear the fence? No. Okay, it was lower than 15 feet. If it was higher than 15 feet coming in here, then it would clear the fence. Okay, if so, by how much? It didn't. Okay, so this is not applicable. If not, could the ball be caught? So thinking about, is this too high for somebody to catch? So you'd think people playing baseball are probably around 6.5 feet, whatever. Okay, can they jump to 13 feet? Okay, so can they jump and get their glove up 13 feet or climb the wall a little bit? So I would say this has a possibility. Okay, could the ball be caught? Maybe. I think it's possible that somebody could get to 13 feet, okay, with their glove extended, especially if they can climb up the wall. Not likely, but possible. Okay, so I would say maybe for that one. Now, if the wall was like 30 feet high and the ball was 27, so it didn't clear the fence, but it's still 27 feet high, probably not catchable. Okay. All right. Then let's take a look at this one. So this one is a foot race. Okay. So Ben can sprint at a rate of 24 feet per second. Jerry sprints at 20 feet per second. Ben gives Jerry a 10-foot head start. These parametric equations can be used to model the race. So we see in this one, we've got the 20. So this one is Jerry. And Ben is sprinting at 24. Okay, so this one is Ben. And Ben gives Jerry a head start. So Ben starts 10 feet behind him, or 10 seconds behind him. No, 10 feet, sorry, 10 feet behind him. Okay, that's where that minus 10 is coming from. So we're gonna, this is talking about how we would type this in our calculator. Okay, so in this first race, we're just so that they aren't on the same spot on our graph, we're gonna put all the Y values of this first one of Jerry at 3. This is just to get it in the correct position on your calculator when we type it out, okay? And then this one, for Ben, we're just gonna put him in on 5, kind of like lanes, like when you're running. So Jerry's running in lane 3, Ben's running in lane 5, okay? And then, so we're going to be plugging in some different times. So it says, this is feet per second. So we'll do, the starting, okay, initial 0, 1, 2, 3, 4, 5, 6 seconds and see, okay? And so let's see, the parametric equations can be used to model it. All right, so let's plug this in. So we'll plug in 0 to x1. So 20 times 0 is obviously 0. 20 times 1 is 20. Okay, 20 times 2 is 40. 20 times 3 is 60. 20 times 4 is 80. 100. And then 120. So this is how many feet he went in 6 seconds, 120 feet. And then let's do the same ones for Ben. And so at the initial time, okay, that we start going, and Ben's going 24 feet per second. So initially Ben's at -10. He's starting from behind, right? He gave him a 10-foot head start. After 1 second, so 24 times 1 is 24, minus 10 is 14. Okay, then 24 times 2 is 48, minus 10 is 38. 24 times 3 is 72, minus 10 is 62. Okay, then times 4 is 96, minus 10 is 86, times 5 is 120, minus 10 is 110, times 6 is 144, minus 10 is 134. Okay, and then this is how far they are kind of on the course here. Okay, so then if we wanted to analyze this and see what was happening, okay, you can see the horizontal distance here. So after 1 second, Jerry is still in the lead, right? He's still in the lead. Ben is 6 feet behind him. After 2 seconds, Jerry's gone 40 feet. Ben has gone 38. Okay, so Jerry is still leading. After 3 seconds, Jerry's at 60 feet from the start line, and Ben is 62. So at 3 seconds is when the lead changes, right? When he overtakes him because he's going significantly faster than him, 4 feet per second faster, right? So if this, if they were racing to, less than 60, Jerry would win, right? But anything past that, Ben is going to win. He's going to be able to get that 10 seconds back. All right, famine relief airdrop. So a relief agency drops food containers from an airplane on a war-torn famine area. The drop was made from an altitude of 1,000 feet above ground level. Use an equation to model the height of the containers during the free fall. Okay, so height was our Y value equation. Okay, and that Y value, remember, is -16 t squared plus the speed or initial velocity times sine of the initial angle of the drop times t plus the initial height. Okay, so when we look at this, we'll have the -16 t squared. And then what's the initial velocity? Okay, so if you throw something, okay, what is the speed that you threw it at? In this case, they drop the bag. Okay, so they just let go. They just reach their hand out, let go. So they're not throwing it. So the initial velocity is actually 0. Okay, so your initial velocity, you didn't add any speed to it. You just dropped it and gravity took over. So you're doing 0 times this whole thing. So this whole thing would be gone. And then the initial height was 1,000 feet above ground. So we'd have plus 1,000. So this would be our equation for the height. So use parametric mode to simulate the drop of the first 6 seconds. So you would be using a graphing calculator for that. And then for part C, it says after 4 seconds of free fall, the parachute opens. How many feet above ground are the food containers? So this one we can just plug into our equation. Okay, so this equation we're just going to plug in after 4 seconds. So we're just going to do negative 16 times 4 squared plus 1,000. Okay, so negative 16 times 16 is negative 256. So this represents actually how many feet it's dropped in 4 seconds. And then you have the initial height that it was at, right? So you have 1,000 minus 256. And so the height when the parachute opens is at 756 feet above ground.